Yeah. So you need to line up some people to assume that you're going to be proactive. You need to be proactively seek speakers, okay? They come and speak to me, okay? And get contact. First, to get this student sign up particular day, okay? Can you do that?
Prepare some speakers?
Yes, we need a speakers with paper, etc. Right?
Okay.
So this student currently not here today, but went back to Beijing. Beijing, right? You're student in Beijing now. In Shanghai. Okay. Okay. Can you follow up with the topics that the student to get get her to space a day? Okay. We also need to have others join. Then, do you want to give a presentation or you prefer not?
Yeah,
maybe later. Okay. The overview talk is earlier the better, right? The overview talk because get people oriented. Okay. So you are first off Robert Tay, and what about you? You just joined. Okay, can you describe yourself? Young Shanghai student. Okay. Second year also? Okay. Good. Okay, where did you do PhD? Okay, okay. Good. All right. So let's should be thinking of Zoom should be working, right? Yeah. So people can, but nobody else. Nobody else. Okay. Really? Can you hear me? Those people
Yes.
You can hear me? Oh
yes, I can.
Good. All right, good. So I'm an all right. All right. So it's good. You do a good job to start pushing us to start this seminar series. It's timely and it's there's a lot of interest here on this campus. Okay. So
Yeah. The voice actually is low. So.
Voice is low. Now better?
Yeah. Now it's better. Yeah.
Okay. Yeah. So I'm going to now hold this one here. I'll talk to this. That's fine. Okay. It's funny. Okay. So next time we will better equip this. Okay. But I still Zoom is it's remarkable, right? You can do this thing. Yeah, yeah. Cool. Next time we do that. So I'm okay. So today is I'm going to start. This first lecture. Basically, give the foundation. They're talking about foundation of the related reinforcement learning, and I think later, but for one thing, just to unify the terminologies, right? And later on, a lot of things going on, a lot of papers, and maybe people using different terms. So sequential decision problems, right? We're dealing with a decision one at a time, uncertainty or action being taken, then the state to move to the next state. So let's talk about this. I'm thinking about N is a time horizon, decision time, and indeed most of the talk will be N will be equal to infinite. Okay. So this N is a decision time horizon, and the notation SK in the literature sometimes using S is a common symbol, right, for state. SK is a state at time K, and we assume that the state is observable. I'm not getting into partially observable. I assume state is observable, and you after observing state XK, you decide take action to take. Okay, AK, and it's taken, and given taking this action, then in the next time period, the state will move into a new state, SK plus 1. And while you move into the new state, you incur a cost or reward. So here I use the term consistently using cost. Cost depending on your current state. You take this action AK, And the next state will be go to xk plus 1. That's your cost, okay, in general. So the sequence often is called episode, right? So the term that is something, so you start from initial state and take action A0, then another state, X1, A1, then eventually at A1, then you get observe state X2, etc., right? Think of, example, maybe in DD platform, right? Ride-hailing, so each time period, suppose you say each 1 minute, I mean, DD perhaps doing decision like continuously, but think of every 1 minute you make decisions, right? So you have X is a state, is how many passengers, how many customers request ride, how many cars are around, right? That's a state. And what's the state of each driver, right? How many each driver, where they are. So that's a state. Then you decide action. Action is the match, right? Matching the passengers with the drivers, okay? And then we're moving to the next time period. We're moving into different state because a new arrival will come in, right? Or a trip will be completed, etc. Right? So that's a new state. All right. So that's so one episode meaning each day, right? For DD for Shenzhen. One episode, 1 day. Tomorrow is another day, another episode. That's clear here? That's a decision problem, okay? So, all right. So the total cost of episode is just adding up the cost of the each period, right? That's random in general, right? Depending on scenario, depending on episode, okay? So a policy is PAR is known as a policy. If a policy basically tells you what action to take on day K, right, at time K. So AK equal to mu K. Mu K dictate how do you, at the state XK, you observing state, mu is a mapping, right? Is a mapping tell you what action to take, okay? So this, as I said, in DD setting, that maybe it's matching, right? It's matching, okay? And the mu K is taken from state space to action space, right? Action space. Because at the time K, you don't know what state may be tomorrow, right? You don't know. You have to, policy is basically is a contingency plan. Once a policy is given, then the human can get out of that, right? Or you can, as a boss, you can take a vacation, right? So whoever executes that according to policy, right? Doesn't matter tomorrow what state will be. That person will know how to act. Is that clear? That's a policy here. So expected cost here, that's written here. And the expectations over randomness over transitions. So they are randomness because the transition from SK to XK plus 1, they are randomness, right? So that's the expected value here. And so that's the expected cost. And under the policy, okay, under policy. And now to do any analysis or to make good decision, you need a model, okay? You need a model here. And one possibility here, we assume that the transition here from XK to XK plus 1 is governed by, if you're taking action A, is governed by this transition probability. PK, K is time period K, and A is the current state. You take action, the chance go to state Y, next day. Is the notation clear? K is the current day K, X is the current state, A is the taking action A, and the Y is the next state. So the chance for that thing happen is P, okay? So there are many cases here, at least here, case 1, transition probabilities are known. Okay, transition probability known. In this setting, the so-called Markov decision process, the term we may not hear a lot about here, but in literature, there's a huge literature on MDP, Markov decision process. That's basically a dynamic programming. That's in this category. The transition probability is known. In reality, often this transition probability you don't know, right? In DD case, or you need a lot of data to estimate them. Okay, you don't know. Okay, so the transition probably don't know, but the second case, the episodes can be observed, right? That's the one here, episode. So that's from data. That's basically you just only have only observations from data, right? From here, that's one. Third thing is I think we are, this is the in between, okay? Third thing, transition probability unknown, but given SK, AK, SK plus one can be, next state can be sampled, can be simulated, can be sampled. So there's a machine there that can be sampled as often as you need, okay? That's sort of ideal situation, laboratory, right? It's in your lab, you can do this, sample that. And that's wonderful. A simulator available is wonderful for your case algorithm, etc. Right? So that's the thing. Because the case to real world experiment is very expensive, right? Sometimes it's not, you cannot afford to do that. Okay? So I have more points to make later on. Okay, in case 2. So let's see. So the objective is optimal value function find policy to minimize expected cost, okay? Expected cost, and so any policy pi star can achieve this minima, okay? That's optimal policy, right? But I want to emphasize in general setting that there may be no optimal policy because that infima cannot be achieved by any policy, okay? And I'm not going to focus on that, okay? So that's, then you talk about epsilon optimality, etc. okay? So, but I will talk about the positive results, okay? Which for practical purpose, maybe it's not very relevant. You can just ignore that, okay? So solving this equation, solving that problem, optimization problem. If n is finite, then and the model is known. Model is known, meaning PIGs are available to us, transition probability. Then the algorithms are it's actually quite easy to find the optimal policy and optimal cost, okay? So the algorithm is called famous backward induction, okay? Backward induction, so or dynamic programming principle. So this is the key to dynamic programming principle, but for those of you who have not seen this, let me go over this. So you start with the last period to the end. If you are, this JK is known to be cost to go. You're currently in day K. What's the total cost from day K to the end? Right, day K to the end. So that's a cost to go function, okay? Ultimately, I want to solve the problem from day 0 to the end, right? But in between, I need to know to solve something from day K to the end, okay, cost to go function. And obviously, if you at the end, the cost is 0 to n plus 1, okay? Then you can do the Jn the next day. You know that, okay, so if you solve so this one here, from day K to the end, what's optimal cost? Where you have some immediate cost, if you take action A, that's immediate cost, right? Plus the future remaining cost under the optimal way from the K plus 1 to the end, okay? So K cost plus optimal cost from K plus 1 on. Is that clear? And you take the action of a different scenario, right? Here is a different possibility, right? Averaging this expected value is meaning because next day K plus 1 can be different possibility, right? On day K, you are in X. So you take the action A. You see, take the action A that minimizes this one. Okay. So this actually, let me just say one more thing here. This is the dynamic programming equation. It's basically allow you to do trade-off. Most people want to minimize this one, right? Immediate cost. That's day K. I want to take cheapest one, but that's may not be optimal thing to do, right? If you take day K cheapest one action, you could increase the future cost, right? You could increase that. So dynamic programming, all dynamic programming doing is to do trade-off. Should I greedily to do the cheapest one now, or when I make action now, I need to worry about future, right? If I make a decision now, even though today's decision is more expensive, it gets me to a better state, cheaper state in the future. That's better, right? So this is the same thing with AlphaGo 0, that if you make the move, this move may not be immediately, you need to take this move, need to worry about the next position is that have better chance to get you to winning, right? So you need to make this kind of decision, okay? So this is a trade-off. Is that clear? Dynamic programming is tell you clearly how to make trade-off, okay? You take the action A so that to provide you best trade-off, okay? I hope it made it clear here, okay? So you do the backward induction, eventually G0 is the optimal cost, okay? Now that's cost function. So how do you take action at day K? Well, day K, you take action whichever A minimize this. That's the optimal action to take. Is that clear here? So whichever A make it. So optimal action may not be unique, right? May not be unique because there are multiple action taking which is attains this minimum. Okay. All right. So the complexity is listed here. That's if a state space is huge, action space is huge, and the time horizon is long. This is a huge amount of time need to number of operations to complete this backward induction. Is that clear here? Okay. This is not counting. This is not counted. Did we already counted this how many action? Okay, so here, yes. So I assume doing the exhaustive search here. This summation take X, suppose X doesn't depend on K, okay, space. How many states, this is how many steps you needed, right? How many actions or how many states you have. So this summation, that many complexity, and then you need to choose, do the search, okay? The action space. Of course, there are special cases, you have a way to speed up this search, but I'm not getting into detail that. The whole thing about dynamic programming is this thing is here two challenges. One is that this P may not know, right? May not know. That's one challenge. Second is the complexity, curse of dimensionality, right? So that this algorithm is useless because the state space is too large. Okay, so that's the thing here. So for the focus of most of talk, a lot of work is to in a way to look at a simplified problem. Look at this infinite horizon, n equal to infinite. N to infinite is simpler. Simpler in the sense by assuming that the time homogeneity. So this pk doesn't depend on k. Okay? And the cost gk is this one is called discounted cost. And g here does not depend on k. Okay? So this turns out can tremendously already simplify problem. Okay? Simplify problem. So I have a time homogeneous system. Okay? Time homogeneous system. And in this case, very similar. This one reduced to the previous backward induction problem to solve the optimal decision problem, reduced to this one. This one is known as Bellman equation. Okay, so you see here it's very similar. Okay, J star is the total cost, right? Expect total cost equal to the immediate cost plus discounted future cost. Is that right here? Because this y is the future state, right? Current state is x, taking action A, y is the future state. So this is the immediate cost plus the future cost from next day onwards, right? But the next day onwards, you have discount factor by beta. Is that clear here? So that's the reduction from the backward induction here. All right, so I have a more maybe more detailed one for the next slide. Okay, so this is indeed mathematically can be proved. So now the notation is a bit, let's get used to. I mean, one thing about these things is these papers are to get over the notation, okay? So this is, I'm repeating the Bellman equation, okay? Bellman equation here. So the right-hand side is some space value. Previously, the summation, right? Summation. But summation is really equal to the space value here. So this is the immediate cost, okay? Plus future cost, right? Future cost. And x prime is the next state, okay? Next day state. Next state is, of course, random, right? It's random. But the random following this distribution, okay? Following distribution. So we know how to take space value. And that's precisely written down here, right? So that's the space value. That's equal to summation, weighted average. That's the space value. So just a shorthand notation for this summation. Sometimes, depending, if you prefer to write down the summation, that's fine. Okay, same thing. But to writing down space value has actually important implication later on. We do sampling. It's very naturally how to do sampling. Okay. Is that okay here? This notation? Okay. So what's the claim here? This theorem says that if state space is finite and action space is finite, so let's maybe consider that. That's the nice case. Okay, that's a nice case. Don't worry about other cases for the moment. So remember earlier we defined G star is the optimal value, optimal cost function, right? Optimal force function. This optimal cost function satisfies this equation. Okay, satisfies this way. So another way to say is a solution to this Spearman equation, right? Is one of the solutions, right? Okay. The second statement is that this Spearman equation has a unique solution. Okay, the two separate statements, right? So which means this G star optimal cost is one solution and the only solution to this Spearman equation. Okay, so here is so how to solve this optimal control problem, optimal MDP problem? Well, first find a solution to this Spearman equation, right? That's number one. Then from the Spearman equation, once you have a solution, solution to the Spearman equation G star, I can find policy. Policy is to seek whichever action minimizes. Okay, whichever action minimizes, that's going to be an optimal policy. Again, optimal policy may not be unique. That's okay? Okay. So, the claim is that a stationary policy is optimal. Okay, stationary policy. Now the term stationary policy, later on I will drop stationary, okay? But once we say setting, we always, the policy really meaning stationary policy. Stationary policy meaning it doesn't depend on which which day you are on. You always using the same mu, okay? Mu does not change with time. Remember earlier, the first problem for DD problem, it indeed, okay, is the DD platform should be time homogeneous and time non-homogeneous. Non-homogeneous, clearly it's a rush hour phenomenon, right? So the time homogeneous is not appropriate there, right? So there for each period of time, you have to use mu k depending on time of the day, right? Hour of the day. But here is because we assume everything time homogeneous. Therefore, there is a possibility that stationary policy can be optimal. Okay, so this one is indeed this policy is optimal. Okay, stationary policy optimal. Is the first part the Spearman optimality result is clear? That's clear, right? Okay, so this is the second. Now I want to define this notation, okay? Because this shows up a lot. This is important, okay? This is very important here, notation at the bottom of this slide. Okay, Tom, you can hear me okay? Hello?
Yes, yes.
You can hear me okay?
Yeah.
Okay, good.
Yeah.
All right, good. So this is given a function h. H is a function it's a function on state space, okay? Given any function, you can choose any function. I can take the minimum of this one here. This is so-called Spearman operator, okay? I will introduce next time. And whichever actions minimize this, I call the mu h of x, mu x, okay? So this define a policy, okay? This define a mapping from state. At every state, I know which action to take, right? Whichever action is minimizes is going to be defined to be the action to take, okay? And this one clearly depending on the h given, right? H given. So this is called H greedy policy, okay? So what is H here? So essentially we know this G is immediate cost, right? H is in this setting is ideally would be approximate future cost, right? Approximate future cost. So if you have some idea, heuristic, some idea of the future cost, you put down here, plug into this H, then you can likely will generate a good policy. Okay? This H will tell you how to make a trade-off, right? The trade-off. And but at this point, it's mathematically just defined this way. Is okay? Okay, so now here we talk about the Bellman operator. So given, earlier I used J, given J, okay, given it's used to be H here, I define this one, Tj is this one here, okay? So this mapping a function J to another function, Tj, okay? Okay, so, and whichever minimizes is whichever policy action takes this minimizes, that's the greedy policy, right? The J greedy policy. Okay, so that's definition. Now here I didn't specify talk too much. This A of X. A of X is the action allowed in state X, right? That's set of actions. Now suppose I'm given a policy mu. Stationary policy mu. If the only action allowed is a mu of X, okay? Right, that's allowed, that's a possibility, that's a spatial problem. You reduce the problem, there's only, at each state, there's only one action allowed, that's mu of X. That's mu MDP, right? That's one. So this one will reduce to this one here. So in this case, you define a Bellman operator associated with this policy. Okay, is that clear? So every result about the Bellman operator also apply to T mu. Is that clear? Because T mu is a special case of special version of T, with A of X restricted. Okay, so that's that. Okay, and the last one is a bit awkward. Let's see what's T mu J. Even did I define mu? Okay, so this is a bit awkward. Okay, so let's see last one. What I was trying to say, I promise not to repeat this awkward notation a lot. The last one just once show up because Mark helped me prepare slides. In his first version, he has a lot of these things here. Okay, so let's just decide for one of these. This mu J is what's mu J? Mu J is a greedy policy associated with the J. Okay, given J, mu J, I'm looking at last line, okay, on the slides. Mu J is the greedy policy associated with J, okay? It's a J greedy policy, mu J, okay? And then I apply to this T, this policy, that's here, on J, okay? Is equal to Tj of X, Tj of X. And this you need to decipher maybe offline if you feel struggled, okay? This I find this is not easy to do that. That's good. Very good. Are we assuming determinism? This Bellman policy, this equation says that yes, it's enough to choose a deterministic policy. Now he's referred to what happened. Okay, not good. Excellent question here. Let's see, go back to the here. Suppose here the two actions reach minimum, right? Two actions, okay? Two different actions. In that case, you can which action to take? Yeah, either one is fine. But you can also randomize, okay? You get the two actions 50%. That's also optimal. Okay? So that's a legitimate question, okay? So that's doesn't have to be deterministic, but it can be deterministic, meaning there's no ambiguity. At state X, you must take this action, right? Randomized meaning at state X, you may flip a coin to decide what to do. All right, so as we said, the first order of business now is how to solve the Bellman equation, right? How do you get the J star Bellman equation? Now the easy thing is indeed very easy. Indeed, I should go back to the backward induction. Where is the backward induction? So here, you just do this one here, right? This is homogeneous. You do the JK plus one, you do the JK next one, iteration, okay? Do the iteration. So essentially the value iteration is essentially the backward induction algorithm, okay? So you solve the Bellman equation. So, so that's what you hear here. So this is the T is the Bellman operator. You apply the Bellman operator one more time. Then you have this this basically do the iteration, value iteration, the backward induction like that doing many times. Okay. And the result says that G star, this one, do this value iteration, has a limit, okay? The limit is the optimal policy, okay? Now this line of literature, the proof here, particularly this kind of one, the important thing here, all the math, or most math, maybe all the math is the contraction map, okay? This operator, the Bellman operator has contraction, okay? So let me walk you through one time, okay? So T star, J star, the optimal policy is solving fixed point. J star equal to T J star, right? Fixed point. You want to find a fixed point. So you want to see how far Jn, this is your approximation here. After nth iteration, how far away from optimal one, right? Okay, and this one, J star is equal, so Jn equal to Tj n minus 1, right? That's according to our notation or definition. J star is a fixed point, so equal to Tj star. Is that clear? Now I'm using the fact that T is a contraction map. Contraction meaning this one is less than or equal to beta times you take out T, okay? You get rid of T, but there's a factor beta here, okay? The contraction beta is discount factor, and I get to the next one. Is that clear? Then you can iterate, eventually get to beta n to that one. You see this one, how far the iteration quality, the convergence, depending on if discount factor is very, this beta very small, so this convergence very fast, right? Also, if your initial guess, J is your initial guess, right? Initial starting point, that's your guess, right? Initial starting point. If your initial start point is close to optimal one, then also converge very fast, right? But of course, that's very difficult for in general. Is that clear? So most people want to start work on the discount problem. I haven't talked about other version problem like long run average cost problem, okay? But most people who want to focus on discount problem analysis is two reasons. Discount factor is artificial, want to say that, okay? This is artificial. And people want to focus on this one. The first thing is a mathematical analysis is easier, much easier, okay? Because it's beta there, okay? But this means also some results are weak, okay? Because everything based on this beta, particularly you get something 1 over 1 minus beta show up in the factor constant, then you already feel that's a bit questionable, okay? How strong these results are. Second, for many algorithms, practical algorithms actually do use this kind of model because even though the original problem has no discount, because it's this helping solving algorithm find a policy, a good policy, okay? And then test it on original problem still works well. That's commonly used now, okay? All right. I hope is that clock is accurate? Huh? 9:34. 9:34. Oh, that clock is misleading. Okay. Okay. So let's move on. So okay, the slides here. Okay. So we just talked about value iteration. Value iteration, the complexity is part. That's complexity here. Okay. So that's value iteration. The problem is that mostly in practice not used. Okay, it's too slow. Okay, for convergence. There's also basically too slow. Okay, the complexity issue. Okay. So another thing is the policy iteration. Okay, now that's most important. I want to focus maybe a lot of time on this, because a lot of algorithms later on talk about the policy gradient and everything. It's all related to this policy iteration, okay? So let's talk about this here. So the strategy is given a stationary policy. We first find a GM mu. Oh, this one is a policy evaluation. I'm not talking about the policy iteration yet. That's the next slide, okay? Policy evaluation. I given policy mu, I want to do performance analysis. I'm not talking about optimization. Is that clear? So I want to find the performance of this policy. And performance of this policy, so GMU satisfies this Bellman equation. Remember, fixed policy, you also have a Bellman equation, right? So because it just restricts the number of actions, okay? So that's Bellman equation. This Bellman equation that mathematically, this is just linear system equations, right? So it's a linear system equations. G is given, suppose, and this matrix P is also given. So this can be written as J equal to G plus beta times P mu times J. So the solution is given by this. Identity matrix minus this matrix, inverse equal to that. Is that clear here? Okay. Except that you never do this, right? Because the matrix is too big, you cannot solve it, okay? You cannot solve it. You cannot even store it in the memory, right? So you cannot solve it. So that's the issue, GMU, okay? So a lot of discussion will be talking, a lot of people talk about how to estimate GMU, okay? So I will talk a little bit today, okay? So that's for the next algorithm, next page, I assume GMU can be evaluated, okay? But that itself is a big task, okay? Big task in terms of two things. One is sometimes P is not known, right? P is not known. Second thing is even P is known, it's too big, okay? Complexity, computational complexity issue, right? So there are two complexities. One is the sample complexity, another computational complexity, time complexity, right? Okay. Okay, let's see. So the policy iteration. Policy iteration is a guessing initial policy, mu zero, all right? Choose a policy, okay, stationary policy. You do policy evaluation, find J mu k equal to 0, say. That's okay? Then, okay, like say solving the system equation, right? Then we do the policy improvement, right? Policy improvement. How do you find a new policy? New policy is to find this J mu k greedy policy. Let's get you a new policy. Is that clear here? That's the mu k plus 1 greedy policy. Once you have a mu k plus 1, then you can find the new policy evaluation. Then you get a new policy, again, to policy improvement, etc. Is that clear? Okay. When do you stop? When you stop, when the two policies give you the same value function. Okay, in that case, you already found optimal policy. Okay, then the mu k is optimal. Okay. Now I want to say that if you go to literature, there's so-called actor critic algorithm, right? Reinforced learning, and that's essentially doing something. I'm going ahead of myself. Okay, so some of you will talk about that later on. That's basically doing it's a version of the policy improvement, a policy iteration algorithm. Okay, all bases, everything, many algorithms, all bases from here. Okay, that's the foundation, the policy iteration algorithm. Okay. What else I want to say that, okay, we need to state mathematical results, okay? So we have a old policy mu k, do the value function evaluation, okay, got a value function for the policy, then you get a new policy, mu k plus 1. And the beauty is that there's this indeed improvement, okay? Indeed, improvement is that your improved policy, new policy is indeed better. Indeed better, okay? Better in the sense that the value function decreases, okay? So less than that. And if a mu is not optimal, strict inequality holds for at least one state. Okay? So if a mu is not optimal, then the next round, it has to be at least one state there's an improvement, okay? Improvement. And this is the basis for convergence. If the action space is finite, then this theorem will guarantee the convergence because as you cycle through policies, if action space is finite, the number of station policies are finite, right? Is finite. So after you go through the number of action policies, it's going to be get smaller, smaller, smaller. Okay, and so it has to eventually reach optimal policy. So any issue with this? It's okay, right? All right. Okay. Now I want to say also difficulties. Okay, immediately, because we said nobody can solve this value function exactly, right? For the thing, either have to use a sample approximation, or because the computational time we need to use other approximation using the neural nets or other things to approximate that. Once it starts to approximation, with the approximation architecture, everything is gone. This thing is not true. You cannot, right? What you wish to be true is not true anymore. And that's all the difficulty comes in, okay? So it's basically, it's valid this, okay? If this is approximation, this is also approximation, both sides the approximation, although they're using same architecture, same neural networks, but the inequality cannot be guaranteed to be true. Is that clear? And that's caused all the problem. That's caused the convergence is so difficult. It's unpredictable. Okay. Right. So some terminology. I think maybe this is even not maybe standard, but this way I view that, right? So when the model PG transition probability known, model parameters known, basically. If model parameters known, this is in dynamic programming setting. People talk dynamic programming and or MDP, okay? Markov decision process, MDP, Markov decision process. When this is not known, environment not known, this is in the reinforcement learning setting. Basically, you have to base on samples, okay? Samples or data to make to solve the decision problem. All right. So now let's talk about the policy evaluation moment. This is setting stage. The next stage, I'm talking about sampling, okay? Something, because assuming P and G are not known, okay? So you can only obtain from samples. So, and also getting into this terminology, TD learning, temporal difference learning, and Q learning, okay? So let's get to that. So recall that given policy, this is the total cost for the policy. Is that clear? This summation, this kind of cost. Remember that? All right. Of course, you can evaluate this by maybe taking many episodes, right? From 0 to all the way to infinite. That's one episode. Another episode from 0 to all the way to infinite, right? Many episodes. You averaging over that. That's called a Monte Carlo method. Right? You can do that. But that's the definition. Okay. So this one, GMU satisfies the Bellman equation, right? So immediate cost, immediate expected cost, okay, plus future expected cost, okay, future expected cost. So the Bellman equation, and for that matter, I'm getting ahead of myself. That's called one-time step Bellman equation. I look at just first step. Today's action makes this today's cost plus future cost. Okay, that's the one-step Bellman equation. Now, the value function is just fixed point for this one. If you can solve exactly, you can solve it exactly, no problem. There's no ambiguity. That's only one GMU satisfies that, right? Now, suppose that you cannot solve this exactly. Then this approximately. Now you have to measure the difference, okay? Difference, measure the error. Now, once you begin to solve approximately, there are many different ways to measure measure the error, okay? So let me just, to set the stage for next one, I want to say that solving fixed point GMU is equivalent to solve this equation, this optimization problem. Because J is the unique J is a unique solution to this fixed point. J mu, J is a unique one, unique for this, J is equal to T mu J. That's it's a unique fixed point, right? So if J is a value function, this is equal to 0, right? Difference is equal to 0. If difference is equal to 0 for every x, that J is a unique, that J is a value function, right? Because it's a unique fixed point, right? If J equal to this for every x, then that J is a fixed point. So that's a value function. So this is no problem, right? So this J mu is equal to the function, whichever function J minimizes. Okay, minimizes. What's theta of x? Theta of x is just positive weight function, right? Here theta can be for anything. You can put anything theta there, right? This is still true. This is only assuming that you can solve J exactly, then this is equivalent, no problem. But as I said, in reality, we cannot solve J exactly, right? You solve approximately. Then which theta, which Xi or which Xi you put down here matters, okay? Which weight, okay? Another thing is, so let me get on to the next slide. So-called loss function. So we are here using this as a loss function, right? So this is a square missing here. There's a typo here, okay? That's square. J minus T mu. That's, okay? So we try to minimize this, right? Minimize this square. This is the J minus this part is a Bellman operator one, okay? J minus that. And this is known as the Bellman error, okay? So let me repeat. When you can solve Bellman equation, exactly there's only one equation, Bellman equation to solve. Once you have to solve approximately, there are now many millions, infinite many ways that can solve approximately. And the task, first order task is to find a loss function, okay? A loss function. And this is one way to define loss function. It's not a unique way, okay? Bellman error is one way to try to measure the quality of your approximate solution. It's not the only way, okay? But it's a popular way. Okay. So, and how do you choose Xi? Well, one possibility is this weight will be different state will be weight differently, right? If a state is commonly visited by this Markov chain, by the way, fixed policy, you have Markov chain, right? Markov chain. If a state is commonly visited, it's visited very often, maybe that state is more important. So you should weight it more, right? If the state rarely visited, you really don't care how far the Bellman error is, right? So, I mean, depending on application context, okay, of course. So one popular choice Xi would be station distribution of the Markov chain, right? That represents the frequency of each state is visited, okay? So, so many algorithms will be depending on that choice, okay? Xi, and of course, at this point, you wonder, I mean, how can I possibly, this Markov chain is intractable, right? How can I find this Xi, right? Cannot be found. No, you don't need to find Xi, right? This we are setting up a stage theory. Later on, you will see actually do the actual algorithm. You don't really need to know Xi, okay? This no Xi is just for the benefit of analysis of algorithm, okay? All right, good. So far, so good. I think I'm running the slide. Look at the slides. And how many? This is 45 now? Or 50? 50. So what I'm going to do is maybe giving some overview. And then for those people need to leave on time, 10 o'clock go there. And I assume some of us here can stay a bit longer so I can get finish the slides, okay? So that's that. Okay, so the first thing I want to explain TD learning, okay? So the TD, I'm motivating. basically the previous optimization problem, I take the gradient, that's going to be equal to that. D is a diagonal matrix with the c in the diagonal, okay? So that's the D matrix times this vector, okay? This vector equal to 0. How do I get this? Is take the gradient of the previous quadratic function in terms of loss function, right? Loss function quadratic, okay? So one way to solve that the Bellman equation to do this iteration, okay? J equal to that, this one here, and times gamma, that's you can solve fixed point. If this has fixed point, then J is a satisfied Bellman equation, okay? So let's see what's, okay. All right, so, but this one is assuming everything P and mu, everything is a known, right? P is a known. So I now wanted to get to the part that is not known, do sampling, right? So the sampled version is, notice that this one is equal to same thing as the expected value, right? This one here, the red part, is the expected value equal to J, that's J, minus G is this one here, plus P, P times J. P times J, that's the expected value, okay? That's the expected value. All right, so this part requires, this iteration requires to know P parameter. Now the next algorithm here is that we're going to do the sampling, okay? So the algorithm is the following. This is called tabular. Tabular meaning that the value function can be recorded at every state, okay? Value function can be remembered in memory for every state. Is that clear? That's a tabular. Sometimes that state too big, you cannot remember everything. You have to use a low-dimensional representation of that value function. Okay, that's the approximation. That's not a tabular. Okay, tabular is everything. So, we start with a. So I'm going to sample the version of what? Is this a value? Yeah, sample the version. I would say value. We are talking about approximate policy evaluation, right? We still in the fixed policy to do the evaluation, okay? This is approximate version of that. So start with J0 and take if you observe XK, that's your current state. We have given mu is our policy, current period policy, so you know which action to take. Once you have action, you can observe next XK plus 1, next state. Is that clear? Next state. And this is the random, right? You can sample that, okay? The next state. And the encode GK, next state, GK, that also can be sampled, okay? So now you update, okay? So GK plus 1, you want to update the value function is equal to previous value function and some adjustment here. So step size, the gamma K step size, and this difference. This difference is at the XK, JK is the current, at the current value function at XK, okay? What's this in the second term, minus this square in the parentheses? That's the next step. That's if you move, if this is the GK, the current cost, plus future cost, okay, future cost. And this difference is called temporal difference, okay, temporal difference. Okay, the temporal difference. So this is XK here, and this is remember here, JK is the same from the previous iteration, okay, JK, okay? And the JK is fixed, and this one is a temporal difference, okay? This is called temporal meaning time here. SK plus 1, okay? The temporal difference. And for, that's just update for one location, very locally update, okay? Very locally, just update for XK. You observe XK and pick one sample, XK plus 1, then you update one location, value function. All the other location of the value function, you don't touch. So it's very locally, right? You very locally. And then you move on, okay, this way. Is that clear here? Here, this algorithm, we didn't need to know P. We didn't need to know G. Everything can be observed from bar samples. Okay. What else I want to say here? Okay, I want to say that in the challenges using the neural network, other approximation later on is this here, right? Once you do that thing, you update the neural network one update parameter, then you do every update of parameter is changing globally for all the states, right? The impact on every state. Okay, here's update locally. Okay. So this is one of the results, convergence result, and this is the standard. I mean, maybe we should have somebody give a overview of the stochastic approximation, okay? Because that's the foundation to prove this thing here, okay? These results, okay? So if the learning rate is decreasing, set for these conditions, then this one will converge almost surely, okay? Almost surely. I do want to mention that I think Mark will go to the next talk to talk about TD lambda, temporal difference lambda, okay? And the good way to, it's a similar algorithm, okay? A better convergence property often, but that's need to be more further discussed. So this is L step Bellman equation, right? You can do the L step here. So the cost of first L days, L period, plus future cost, remaining cost, right? That's the Bellman equation. Okay, and then from here you can devise similarly the algorithm, okay, the learning algorithm. And what about this L is random? Okay, we can pick L is random, L is a geometric random variable with parameter lambda, okay? Lambda is the success rate, okay? So if you do the L random sample randomly, okay, and a corresponding algorithm coming out, that's called TD lambda, okay, TD lambda. So the TD lambda, I hope Mark can be motivated from there, okay, get the formula. Otherwise, you see the formula is very mysterious, okay, TD lambda, very Q factor, that's the last topic, okay, the Q factor here. We are already 10 o'clock, right? So I have for this, you need to go, you feel free to go, okay? So I just the last few slides talk about the Q factor, okay, Q learning. Because temporal difference learning, that's the issue, that's only for policy evaluation, right? And you still need to do policy improvement, right? Those things, okay? So temporal difference, I mean, the Q learning factor is really, it's more direct way, okay? More direct way. Direct way meaning that, okay, so Q star, define Q star, so suppose J star is the optimal value function. We can define Q star this way here, right? Q star, the meaning of Q star is that this immediate cost, right? Q star is the argument means it's a function of X and A, a pair, sometimes called a state action pair. State action pair, is that clear? The state action pair. So the Q star is a function of state action and is equal to immediate cost plus future optimal cost, right? That's the Q star, okay? So depending on, so the immediate cost depending on your action, right? But action is already known which action to take. That's A here, immediate cost. So I have no problem to decide today what to do, but I don't know what tomorrow will do, okay? Tomorrow is going to be the optimal one. But in general, I don't know what's optimal one tomorrow, right? That's tricky. So people so-called roll out policy. Roll out policy meaning that, okay, from tomorrow on, using some heuristic, right? Some heuristic. Today, I'm going to use action A. I'm going to use Q star, a different version Q star to decide optimal way to do today, right? But assuming tomorrow will follow something, okay? follow something. That's going to be replacing here. Okay. So anyways, that's definition clear, right? That's definition clear. And if you don't know the P, then you do sampling, right? You do sample from X, this p value is in terms of for next day, X prime, right? Next prime. You do sampling, sample IRD, XI, prime IRD, then you do sampling. Is that clear here? That's if you don't know the, this is just sampling for one day, right? Just one day, okay? From X, you repeatedly coming back from X to next day, X to next day, X to next day, right? So that's this is cheap, often it's very cheap sampling, okay? So so you do that, okay? So this is called optimal inference. Inference is you just took X, once you have Q star, you have mu star, that's an optimal action. Is that clear here? If you Q star. So if Q star, if you can remember Q, so computing this can be time consuming, right? Can be time consuming, this stuff, right? Even if you have J star, so let me repeat. Even if optimal value function J star is known, computing this part can be time consuming, right? So, but once you have Q star, it's a much simpler step. It's just to find optimal policy this way, optimal action this way. So imagine a car, let's say self-driving car, right? You're training, learning J star, load into car, load J star into the car. Maybe that's not efficient. Maybe the car may not have enough power to compute the optimal action, okay? But if a car can remember Q star, it's much easier, right? Okay, so that's why there's motivation to directly learning Q star, okay? So in that case, the decision may be much easier. But if action space is huge, then maybe you need to have some approximation. If Q star is too big for the memory, or this optimization problem, this optimization too difficult to solve, then you need some low dimensional representation of Q star, right? So that can be Q star can be stored in the car memory, right? All right, okay. So this is the similar Bellman operator for the Bellman operator for Q factor. You define this operator, and turns out that Q star is a unique fixed point for this. This is very mathematically is equivalent to the J star. If the J star is fixed point, okay, to the Bellman equation, this Q is a fixed point for this equation, okay. So that's quite easy to get. And from here, this fixed point, you just find a Q star through the value iteration, right? From QK to the next one, QK plus one, apply that, okay? Now, in this one written down here, there's a big loop here, right? With K is fixed, there's a loop for what? Every state, you need to do this. Every state is huge. Every state action pair, I'm sorry about that. It's every state action pair. Now, this is just take infinite amount of time, right? There's lots of action state action pair, right? To do that, that's big loop there. So people want to do some optimistic ways. When update part of a state action pair, I got suppose I have QK. And when do this update here, do this equation, I just update some state action pair. Then in that case, you do not really get the K plus one yet, Q, right? You're in the middle of getting into the QK plus one, right? Suppose that's called, in that case, you may be already ready to make decisions, right? Now you make a decision not based on the QK plus one, but partially obtain QK plus one. That's the so-called optimistic policy improvement, optimistic. And that's a lot of these algorithms now in the papers using that version. And all right. So anyways, this one actually you can prove the convergence, no problem because of discount factor, this one. But this one requires to know what? Knowledge P, right? The model is known. Is that clear here? Valuation requires model is known. But once the model is not known, sampling one, you have to do sample, then things are much more complicated, okay? And that's where okay? And so there is a mathematical result. Is this on the next slide or what? Yes. Okay, so there's a, so let me state the algorithm. The algorithm is you generate infinite long sequence of xk, ak, gk. Okay, this triple. Okay, so you observe state xk, take action ak, record the value function. Okay, okay. And so that each state action pair happen infinite often. So immediately you see, this requires a lot of exploration, right? I need to get every state action pair need to be appear infinitely often, right? A lot of exploration going on. So in particular, if you use similar Markov chain for fixed policy, you have Markov chain, right? Fixed policy, like today, like DD, I'm always using the closest match, right? The passenger and the driver most closest match, that's not enough exploration, right? That's just one particular policy. And a particular policy, you have visited many other state action pair, right? But that does not satisfy this equation, this assumption. Am I right? And a particular fixed policy, this assumption is not, even if you observe the sample for infinite long, this equation, this assumption is not satisfied. So you have to intentionally do exploration, okay? To pick that state, this state from various state, okay? So the mathematical result says this just provides some suggestion inside, right? Inside. So how do you achieve that? It's not issue, okay? So that's, you just do this, assume this can be done. Then the Q factor is updated this way, one sample at a time. For pick xk, ak from the sequence, okay? Then you just generate a new next state, xk plus 1. Because here, xk plus 1 may not be the child of the previous xk, right? Because the Markov chain could be restarted by exploration. Restarted the next state could be just exploration, right? It has nothing to do with the next state, okay? So here the xk prime, k plus 1 prime is the next state of xk, okay? And then do this algorithm, you update one locally at one location, keep other location fixed. This algorithm is indeed convergent, okay? The convergent, that's the next one here, and that's considered to be big results, okay? That in the 90s. So this algorithm converges, this way converges to Q star, okay? So this is pretty much that one of the few results can be proven to be convergent, okay? All others will be, now this is under the tabular representation set, right? Remember, for most of our practical problem, the tabular representation is not feasible. Just too many state action pairs, right? Too many of them. So once you get into the approximate architecture, okay, approximation, then everything is fall apart, right? So we are just doing heuristic, essentially, right? That's why this the theory, the reinforced learning is not satisfactory, right? Something, everything is most of them are the heuristics, okay? So why I'm doing this here? Oh, I want to do the policy, want to represent one last algorithm. It's called SASA. That's being in the literature. And this is essentially related to the policy improvement. Okay, so this is the policy improvement algorithm using Q factor, but it's the same as before. Okay, so just using the Q notation instead of using J. Policy evaluation previously using J. So this is the SASA. Okay. So I mean, previous one generate infinite sequence ahead of time. That's not realistic, right? the previous. It's a mathematical result there, but not really. This one you can implement. Okay, let's see that a lot very tempting. Okay, so a lot of you probably will do. Okay, will do. So let's see the algorithm. Okay, Q learning related to Q factor. So you initialize Q0. Okay, I start from Markov chain. Start from some initial X0. Okay. Once I have Q, I know how to make decisions. How? I'll make a decision. So I'm currently at state. Currently, I'm at state xk, right? And okay, so this Q is a step to simulate. One step starting from xk would given so state action pair. So I know current action to take xk. Okay. It will lead to me next state xk plus 1. Okay. But I don't know next at ak plus 1 what action to take. Okay, I don't know, but I can take this action to be this one here, to minimize, because you assume qk is already known, right? Qk is known is to help you to make decision global anyway. Okay, once you have qk is known, right? Once you have one version of q is available, I know what action to take. At least I take greedy one. Greedy one meaning this. But this one is adding some exploration because your initial Q0, Q1 is very unreliable. Do you understand? Q0 is initial just random guess. So it's very unreliable. So we will do here, often you add something, the exploration, right? Exploration here. So now how do you update? You update, this is equal to this here. Okay, so the update one more step is current, take current action plus future. Future is xk plus 1 and ak plus 1, right? Remember that Q need two arguments, right? State and action. State is the next state of xk plus 1, observed. But you also put on action. Without this one here, you don't know what to put in here. Often people put the minimization. I guess one version is to put one version is to put a minimization. Did we put a minimization? What? Oh, back to the value iteration. Okay. But I should say that this SASA, this is the state action reward state action, right? So it's a xk state action, ak state action, gk reward. Okay, reward here we call reward, and the next state is x plus 1, and the next action is the action here, and then that's the acronym SASA here. So that's and it's convergence. I think in practice we don't know. Okay, don't know. And even if you do provide something, maybe the condition is maybe not practical. Okay, so there are a few. So today, I mean, the results there. We try to. I think that good if you put something there. So the first, I mean, slides should be on the website or somewhere so that audience can download and hear the references we use. I think that's all for today. Okay. Any question or comments here? What? 2 more slides. These are slides for proof value iteration convergence. Okay. That's so the one is to prove that the map is contraction. You said this contraction proof. Contraction is where? In the previous slides? No, I think this is just monotonicity result, and this is the way to prove the contraction. Yeah, contraction. What is this a typo? Yeah, that's T. That's a typo, not TK. T. Okay. All right. Is this overview?
Yeah, Jim is very, very nice talk. Thank you very much. For
Oh, just a second. I cannot hear you. Just a second. Let's see if I can.
Can you hear me? Can you hear me?
Marco, can you turn on your microphone? You turn microphone, not a speaker. Turn on your speaker, not speaker.
Okay, I turned on.
Hello?
Yeah, go ahead.
Oh, I just said, well, so there's a lot of echo here. Hello? Hello? Can you hear me? Guess not.
Tom, you can speak.
Oh, okay. Thank you. Just want to thank you for the nice presentation. It's a very concise, very clear. Thank you so much. I just have one question. This especially this is related to this exploration business. So this exploration can certainly impact the convergence, right? The strategy. If you use just an epsilon probability to try something new, and then the other 1 minus epsilon probability, you choose the one according to your current Q function. Right, yeah, right, step 3. Now, how do I mean, certainly will affect convergence rate if it ever converges. Secondly, how do is there any way to ensure this exploration or something new that I try will have a bounded sort of effect on the current policy? Because in practice, the engineers are or system operators are very reluctant to try something new that they haven't experimented before, and then if it leads to disastrous results, they're not going to try it. So I don't see how.
Maybe we can.
Can you hear me? So when you do this reinforcement learning, is there any way to experiment with the new strategy? I mean, new action that gives you a bounded. If it gives you a bad results, I want to make sure the loss is limited, is bounded, because I haven't tried it.
Can you hear me, Tom?
Yes, it's too loud.
Too loud. Okay. Okay. So I think this is the issue with this right. I listed here the SASA is purely heuristic, but this epsilon graded exploration is often throwing the average, right? This average in this paper, theoretical paper. But in reality, right, how do you do random exploration, right? That's particularly in the many settings, the hospital setting, in a patient drug system, you cannot just randomly something because people's life are affected, right? You cannot just randomly choose people. You have to know some.
So if you try something silly in the name of exploration, you may cause a disastrous result to the whole system.
Yes, so, and
how do we sort of do exploration with caution? In other words,
I don't know the answer, but I think this is the question maybe for the audience, for everyone here. So when we searching for future paper, how do people try to that? Maybe Tom or somebody else can have some answer to Tom's question. So it's right. That's a challenge. Okay, Tom. I'm not aware of any results in this regard.
Okay, and also this epsilon exploration. I remember people. I mean, Ben Van Roy talked about Thompson sampling, all this stuff, right? And show that it can make a big difference. But there are also cases where Thompson sampling is not optimal. It's actually far away from it.
Yes.
So it's not clear. So how we should do exploration and the Q learning at the same time.
So these are suggesting the papers. Okay. So let's something. I just here to throw up the tomorrow to basically put hopefully most people on the same page. Right. This is just starting phrase.
So we should keep all this in mind when we study. Yeah. When we study all these papers in detail, we can keep all these questions in mind. Right.
I would just mention that epsilon grid is certainly is one way. Another way is the Boltzmann type of updated. Maybe to me it's more gradual. Right. This may be solving Tom your question. I mean maybe that's more gradual. This is more drastic. Something. Boltzmann type meaning that I'm not sure that people know that basically you do not choose the largest, I mean Z largest one QK, right? You choose the probability. So you see here, all action A can be chosen, but AK plus 1 more likely to be chosen, right? But depending on the value of Q, right? Value Q.
Okay.
It's weighted average. Okay. So that's indeed that AlphaGo 0 is you know the monocology research is essentially is doing that. Okay.
Okay. Thank you very much, Jim. I have to leave for another meeting now. So excellent talk, excellent start of the seminar series.
Okay. Next time, I hope you can join in person. All right.
Yeah, I will.
Okay. Good. All right. Okay. Good.
Thank you. Yeah. Bye.
Bye.
Sounds good.
Wait. Any others have comments or questions or any comments or something? Because for most, I mean, some of you, I mean, of course, it's too simple because you already know all these things. Okay. So, but are there any questions? Like I think Tom raised some good questions here.
One key issue I think we didn't make clear is what kind of data, what kind of procedure can be used for training, right? Now here, certainly, you have to be able to sample, right? You don't know the transition, but you're able to sample, right?
Yes.
So what if you just have some trajectories from some policies?
Oh, you're talking about off policy, on policy?
Okay. You know, I think that this part is very confusing. People really don't know what the data are being used.
Yes. Can you give a talk on off policy?
I'm just raising this issue here.
Okay. Yes.
Why this kind of things is confusing is that people usually don't sit outside, right, at the very beginning. What are the available data, right?
Yeah.
And what are the procedure you actually use to do this learning process?
Right.
They always assume they know something.
Right.
And then they suddenly say, oh, by the way, you can interact with the environment and get the Nexus data and else. On the other hand, someone will probably just say, oh, I assume you have all these experiences, right? Aren't you using a replay from the experiences or something?
So I think the terminology is important, right? So in the reinforcement learning community, the on and off policy. Here is the on meaning that you use the current policy, assuming data can be generated. But how can you use the off policy, data from another policy? Can you do something, right? Policy evaluation for some new policy, for example. Well, if you have a model, then maybe that's possible. Without model, of course, you cannot. right? We cannot. This may be even related to the transfer learning in the machine learning community, right? Transfer learning. So it's essentially related to transfer learning from one environment, one policy to another policy. Okay. So that's definitely is valid. And then, yeah, please. Any other things, comments? What?
Importance.
Important sampling. Important sampling. Well, the transfer learning, I mean, the our policy is using the important sampling idea. I don't think the important sampling itself. I think bringing important sampling, I'm not sure that's useful or profitable. That's something, right? But idea is there using that change information. Okay, so important sampling often come up with different contexts, and indeed this change information coming from important sampling is from different contexts. Is this accessible, useful? I mean, you guys already read all this, read a lot, right? Now, for the next two talks, they're going to be prepared. The next two talks are also overview things. Is this level good enough? Good? Yeah. All right, good. So we also need to set up a talk. I think this is the application combination of applications and theory. Maybe more errors, but I think driving interesting applications is interesting because particularly they might bring up the new issues like Professor Zhang talked about. Where do you get data, right? The new problem gives you thinking, to put it into this challenges into context. Okay. All right. Good.
So,
okay. See you. We're going to meet next Monday, right?
Yes. The same
Monday.
time.
Yeah. Here.
I think Tom's question was about safe exploration.